Why are the forces T1 and T2 equal in magnitude? This is a question many students find tricky to explain. Let us break it down with a simple example to make it clear. Imagine we have two objects with masses m1 and m2 connected by a massless string. The right object is being pulled by a force F1, and we assume there is no friction between the objects and the table. To determine the magnitudes of the acceleration and the string tension, we will use a standard approach. First, we will identify all the forces acting on the objects. For object 1, the following forces are at play. The force F1 pulls it to the right. The force T1 is the tension force from the string, pulling it to the left. The gravitational force, equal to m1g, acts downward. And finally, N1, the force exerted by the table upward, as the table slightly bends under the object's weight. For the second object, the tension force, T2, pulls it to the right. The gravitational force, M2g, pulls downward, and the force, N2, pushes upward. Now, let's formally state Newton's second law for the first object. The sum of all forces acting on the object equals its mass times acceleration. In detail, the equation is as follows. Keep in mind we only use the plus sign when summing all force vectors, regardless of their direction. For the second object, Newton's second law is written as, or in detail. Of course, in this problem, the forces N1, M1g, N2, and M2g do not influence the motion because there is no friction. However, we include these forces to illustrate the general principle. To move from the general formula to specific calculations, we set up the coordinate axis, draw the free body diagram, and then apply Newton's second law separately for each axis, using the force projections. The most convenient approach to this problem is to align the x-axis with the direction of force F1 and the y-axis vertically upward. In the free body diagram, the forces will be represented as follows. F1, T1 along the x-axis, N1, M1g along the y-axis. For the first object along the x-axis, Newton's second law is F1 minus T1 equals M1a. We assign a positive value to the scalar force projection when the force vector is directed along the axis, and a negative value when the force vector opposes it. That is why T1 has a negative sign. Now, let's write Newton's second law for this object along the y-axis. N1 minus M1g equals 0. The negative sign before M1g, of course, indicates that this force is directed opposite to the y-axis. Since the object has no acceleration along the y-axis, we directly substitute 0 for the mass times acceleration. Let's write similar equations for the second object. Technically, we should use a separate pair of coordinate axes for each object. In the free body diagram, the forces are represented as follows. T2 along the x-axis, N2, M2g along the y-axis. Along the x-axis, the equation is T2 equals M2a. Along the y-axis, the equation is N2 minus M2g equals 0. Since we don't need to use the forces N1 and N2 to calculate the friction forces in this problem, we are left with only two relevant equations. The acceleration a of both objects is, of course, the same. Otherwise, the second object would either move ahead of or fall behind the first. Now, let's examine our equations. we notice some mathematical issue. We have three unknowns, T1, T2, and A, but only two equations. To solve this problem, we need a third equation. Let's turn our attention to the string. The string pulls object 1 to the left with a force T1, and by Newton's third law, object 1 pulls the string to the right with an equal force in the opposite direction. Similarly, the string pulls object 2 to the right with a force T2, and object 2 pulls the string back to the left with a force of equal magnitude. The key idea here is that since the string is a physical object, we can also apply Newton's second law to it. In vector form, we can write T1 plus T2 equals ma. Then, in terms of projections, we get T1 minus T2 equals ma, where m is the mass of the string. Solving for acceleration, a equals T1 minus T2 divided by m. If the string has no mass, then T1 and T2 must be equal. Why? Because if they weren't, the equation would imply that the massless string accelerates infinitely fast and shoots past both objects, which obviously doesn't happen. The answer is T1 equals T2 because the string is massless. This leads to an important general rule. For any massless object, the sum of all forces acting on it must equal 0. Otherwise, it would experience infinite acceleration. Now we can simplify our equations by replacing T1 and T2 with just T. F1 minus T equals m1a, and T equals m2a. To find the acceleration, we can substitute T with m2a in the first equation. And by solving this equation for a, we finally get a equals F1 divided by m1 plus m2. Finally, to find T, we simply multiply m2 by a. Even though the result is fairly simple, let's make sure we have calculated a and t correctly. To do that, we will check how our formulas behave in situations where we already know the expected outcome. Case 1. F1 is equal to 0. In this case, the two objects just sit on the table, so both the acceleration a and the tension t must be 0. By substituting 0 for F1 in the formulas, we get a equals 0 and t equals 0. So, the formulas give the correct result. Case 2. M2 is equal to 0. In this case, there's really no second object attached to the string. So, the string feels no tension from that end, and t must be 0. The acceleration of the first object is then simply F1 divided by m1. By substituting 0 for m2 in the formulas, we get acceleration equals F1 divided by m1, and t equals 0. Once again, the result checks out. Case 3. m1 equals 0. If m1 is 0, the first object effectively doesn't exist, and we are pulling directly on the string with force F1. In this case, the acceleration is equal to F1 divided by m2, and the tension T must equal F1. By substituting 0 for m1 in the formulas, we can clearly see that the acceleration equals F1 divided by m2, and tension equals F1. So, we see that our formulas have successfully passed all the tests and give the results we would expect intuitively. This confirms that we've solved the problem correctly.